Let's talk a little bit more about the locus and the complex numbers. Whilst we've been talking about the Argand diagram, we've seen, of course, complex numbers can be represented by both a point and also as a vector. So let's have another look at circles. There's our basic circle, of course, where the centre is at the origin. And what we said before is we could write that equation as z times z conjugate is equal to the radius squared. Well, now we know a little bit more. There's a much neater way of writing that. Because when we say, what do all the points on this circle have in common? Well, they're all the same distance from the origin. Well, we now have a term for that, and that's called modulus. So the modulus of z is equal to some constant number. What it's basically saying is the distance of z to 0 is always a constant amount. Well, whenever you've got a constant amount from one point to another point, we know that locus is going to be a circle. Okay? If we shift that centre, and what we saw before was we'd see it in that sort of format, z minus omega, z conjugate minus omega conjugate. But again, now we could think of it using this idea of vectors. Z, remember, is on the red circle, and I'm joining it to omega. So if I wanted to label that vector would represent the complex number z minus w. Well, the radius is the length. So what we're really saying is the length of when I join z up to w is always going to be r. So again, you would get a circle. And it's still like our familiar idea back from coordinate geometry. If we shift the centre, we always go minus the coordinates of the centre. Well, it's exactly the same idea. We're going z minus the coordinates of the centre, or in this case, the actual complex number of the centre. So if they ask us to draw a locus and we see modulus equals a constant number, we know straight away, circle. Don't have to do any algebra. I can just look at it and go, okay, I know that's a circle, centre whatever, radius whatever. So we're going to express these circles in terms of z. Well, x squared plus y squared equals 16. We hopefully recognise that. That's our standard circle, centre at the origin, radius of 4. So I could rewrite that as the modulus of z is equal to 4. Or if you wanted to put it in that conjugate format, you'd go z conjugate is 16. But probably the modulus format now is the better way of writing it. I think a lot neater. Okay, over here I'm going to have to complete the square to work out where the centre is. So we'll group the x's together. Half the coefficient of x we want to factorise. So I get x plus 3 all squared. Y minus 2 all squared is 25. So this would become z minus the centre. And the centre in this case is negative 3 plus 2i. So when I subtract it, I get 3 minus 2i. So in fact, the signs actually match up to the algebra there, you'll notice. Because in both cases we're saying minus the centre. The actual centre is not 3 minus 2i, remember. The actual centre is minus 3 plus 2i. Because we're saying z minus the centre. And the radius for that one would be 5. So if we were to draw all the complex numbers, such the distance from z to minus 3 plus 2i was 5, we'd get a circle. And in conjugate form, it would look something like that. Okay, this time we're going to find the centre and radius. All right, well, z minus the centre. So the centre must be the complex number 5 plus I, but if we're talking about coordinates, it would be the point 5, 1. Its radius is 2. Be careful with that, because we're now saying modulus is equal to a number. Remember, the modulus is the length of the vector, or the radius. We're so used to seeing the number and going, oh, the radius is the square root of that. So a lot of people would make that mistake probably and go, oh, the radius is the square root of 2. But remember what format it's in when you're making those decisions. Here's one that is in conjugate form, because I notice the only difference between the two as far as the number goes, this one's 4 plus I, this one's 4 minus I. So it is in that form of z plus the centre, z minus the centre, I should say. Conjugate minus the conjugate of the centre. So therefore, the centre must be the negative of 4 plus I. So it would be minus 4 minus I is the complex number, but as coordinates, that would be minus 4 minus 1. In this case, it is the radius squared. So for this one, the radius would be 7. Ooh, okay. Modulus equals modulus. Don't recognise that one. Still don't. But if it was modulus equals a constant number, we'd know, oh yeah, okay, this one's a circle. So if I don't recognise it straight away, that's when I'm going to break it up into real and imaginary parts so I can get a feel for what the Cartesian form is. But I am still allowed to factorise. So 3, well, I know the absolute value is 3, so I can pull that out of the modulus or the absolute value. We're now saying modulus of z, which is distance of z to the centre, which would be the square root of x squared plus y squared. And this one is the point from z to the point minus 2, 1. So that would be the square root of x plus 2 squared plus y minus 1 squared. I've just got rid of the square root sign straight away, because that would be the first step we'd do. But be careful if you're going to do it in all one step, because remember to square the 3 as well, because you're getting rid of the square root sign. So I've got 9x squared and 9y squared. All right, let's group things together. So expand the right-hand side out, tidy it up a bit. Coefficient of x squared and y squared are the same, I notice. So yes, indeed, this is a circle. But I prefer the coefficient to be 1. So let's divide everything by 8. And now I can complete the square. So it'll be half the coefficient of x and so on. Well, half the coefficient of minus half is minus a quarter. Half the quarter over there with the y is an 1/8. Got to add the square to the other side. So I've got to add 1/16 and also 1/64 to 5/8. We end up with 45/64. There's nothing to say these numbers will always work out nice and neat. But I now can read off that. I know what we've got here. It's got a centre of a quarter minus an 1/8 and a radius of 3 root 5 on 8. I could waste a lot of time here because I could look at it straight away and say, well, look, I don't recognise what it is. And I don't. But there are features there that I do recognise. I know z conjugate is x squared plus y squared. I know z plus its conjugate is always going to give me twice the real part. So I'm not going to waste time by subbing in x plus iy, x minus iy, and tidying all that up. I'll go to what I know, and so that's going to be x squared plus y squared and plus 4x. And, oh yeah, well, okay, well, that's a circle as well. So let's complete the square. We'll get x plus 2 all squared plus y squared, which means I've added 4, and we got it. Centre is minus 2, 0. And the radius is 2. All right, let's have another talk about lines. We talked about horizontal lines. We said, yep, every complex number on there had the imaginary part equaling a constant number. Vertical lines, yep, everyone had the real part the same. They were the simple ones. What about if it is at an angle? So let's just have a look at this. There's a line at an angle. A question that would create a line, a typical question that would create a line is this. If I've got 2 points, what is the perpendicular bisector? That would create a line. Okay? So I'm sort of thinking backwards here to discover what it's going to look like. So I know the perpendicular bisector of 2 lines, 2 points, is of course a line. It's the perpendicular bisector. But what do I know about the perpendicular bisector? Every point on that line is equidistant. Or the distance from z to w1 will always be the same as the distance from z to w2. So I could rewrite that as the modulus of z minus w1, distance of z to w1, is going to be the same as the modulus of z minus w2. So now, thinking about that idea in reverse, if I see something that says modulus equals modulus, and the coefficient of z is the same, that's why I couldn't, oh, it's not there now, but that's why I couldn't do it with the other one, because I had 3z and 1z, so I didn't recognise that one. But if the coefficient of z is the same, I know I'm talking about a straight line. I know it's going to be the perpendicular bisector of the 2 particular points. So here's one. Modulus equals modulus. Coefficient of z is 1 in both cases. I know this is going to be a straight line. Now, I could do it with the distance formula anyway, because remember, this simply means distance of z to this point. So it'll be the square root of x minus 1 squared plus y minus 1 squared will equal the square root of x plus 2 all squared plus y plus 1 squared. And I can expand that whole thing out, tidy it up, and we get our straight line. It doesn't take that long to do. I mean, that's a fair enough way of doing it. Or, as I say, the other way we can now think of it, we say, well, I know this is going to be the perpendicular bisector of 2 points. In this case, the point 1, 1, and also minus 2, minus 1. So I can find the midpoint, so I know it's going to go through that point. I can find the slope between these 2 points. The line we want is perpendicular to it, though. So the slope I want is minus 3 on 2. I got a point. I got a slope. Point slope formula. And eventually we get there. And obviously we get the same answer. Doesn't really matter which way you go. It's just how you're thinking about the question at the time. The advantage of the second one is sometimes you'll get questions where it simply says, draw the locus. It doesn't actually ask you to find the equation. So if I know, it's a perpendicular bisector of those 2 points, very quick to draw the locus. If I don't know that, even though they haven't asked me to find the equation, I'm going to have to work out the equation to draw the line. Here's a really obvious one, as far as if you know it's the perpendicular bisector. Okay, because here it's a straight line. I know it's the perpendicular bisector. Have a look at the 2 points, though. We're saying the distance to 4 on the imaginary axis, so 4i, is equal to the distance to minus 2. Perpendicular bisector of 4 and minus 2. Well, which point must it go through on the y-axis? Yeah. And we know it's going to be horizontal. And there it is, because it's perpendicular to... Never actually asked, what is the equation? Simply said, sketch it. So I can save myself a lot of time if I look at that and I understand what it's saying. Okay, yeah, distance to this is the same as distance to this, perpendicular bisector. Rays. Now, there's a terminology we probably haven't heard for a while. Back in, when would it have been? Year 7 maybe? And we define things as rays and lines and intervals. You remember all that sort of terminology? Do you remember what a ray was?
One point and the rest is...
Right. Has a definite starting point, but keeps going off forever. A line, technically, something goes on forever in both directions, of course, and an interval, definite starting and finishing point. Although we often call that a line anyway, when we loosely say, the line AB. Really, we talk about the interval AB, but we don't get caught up on that. Rays, though, are another matter. Here we go. There is a line. It goes off in a certain direction, has a definite starting point. What does every point... I've sort of given it away by drawing the theta in, I think. But what does every point have in common on that particular ray? Yeah, it's argument. It doesn't matter which point we do, the angle it's going to make. If we made the vector, because that is the vector for every point on that line, if you like, it's always going to make theta. But you notice I've circled the starting point. And the reason for that is, if I'm going to define this as the argument of z is equal to theta, the starting point doesn't have an argument because I haven't started drawing the line yet, or the ray. So how do I know which direction I'm going off in? So a single point where we start the ray won't be included at the beginning. It's not until we join it up to something I can say, okay, that's got an argument of what have you. Now, of course, we could shift this just like we can anything else in coordinate geometry. If I moved it to omega, it's just the angle it would make with the horizontal. And that would simply be z minus omega. Same idea, wherever we shifted the starting point to, minus the starting point. So we're going to draw, this is now regions in the plane, but it now looks a little bit different because we're using complex numbers. It's the Argand diagram. We're saying we're going to draw every number such that its distance to the origin is less than 1. Well, we know that to be inside the circle because it's got to be closer to that. And then the other part, we also want all the numbers such that their arguments are in between 0 and pi on 4. So we've got a couple of rays. So let's draw it up. There's our circle. It's dotted because the boundary is not included, but the boundary is mod z is equal to 1. We know we're inside that circle. Okay, there's my first ray. Argument of z is pi on 4, which means this angle here must be pi on 4. The other one is the argument of z is equal to 0, so the one just going along the real axis. We're in between those two rays. We're inside the circle, so the section must be in there. But technically, we should also circle the point of intersection. Because remember, if it's this and this, the intersection point's not included. Okay. For